Hello everybody. Welcome to the Physics Colloquium. I'm Sterl Phinney, and it's my pleasure today to introduce Peter Sachs Collopy. Since 2017, Peter's been the university archivist and head of archives and special collections here at Caltech. And just remind that those of you approaching retirement should be very nice to Peter, since he'll be the one deciding which of your emails to put on the web. So Peter got his BA in history in 2007 from Oberlin and his PhD in 2015 from University of Pennsylvania on the history and sociology of science. Then he was a Mellon postdoctoral fellow in the digital humanities program at USC. And since 2017, as I mentioned, he's been here at Caltech. Peter's PhD was a preview of the current cell phone video and Instagram generation. His PhD was on the influence of portable videography in the 60s and 70s on psychology of consciousness, narcissism, and psychedelics, among other things. He has way too many interesting articles and essays to mention, but I'll just pick out one here for a physics audience. Peter's been working on putting the Caltech archives on the web, and in particular in physics and astrophysics, the Hale papers, the Glaser papers, the Ahmed Zewail papers, and Ron Drever's papers, for which he has an AIP grant. And he has a nice little review with the American Institute of Physics on the history of physics in the Caltech archives. He has a grant from the Getty Foundation of Seeing Caltech Science for the Pacific Standard Time 2024 exhibit at the Getty, sponsored by the Getty. And today he'll tell us about iterating infrastructure from high voltage to X-rays to nuclear physics, early science in the Caltech archives.
Thank you, and thank you for this invitation. It's exciting to be speaking to this physics audience, a little outside of my usual disciplinary terrain. I'm a historian of science, but typically not a historian of physics, although working at Caltech has pulled me more and more into history of physics because we have such a rich history of physics on our own campus to draw from. And I hope to share some of that with you today. Sterl mentioned some of the range of things that we do in the Caltech archives, and I just wanted to begin with a couple of slides showing off some of the context for the work that is in this presentation. This list is from a few years old, a few years ago, so the online column in particular would now include the Glaser and Hale papers, which we've digitized and have on the web, and it will very soon include the Robert Millikan papers as well. The Hale and Millikan papers were both microfilmed decades ago. We've been able to digitize them from the microfilm, so you'll see some images from that here today. They're not as pretty as scanning from the real thing, but we're able to do it at scale very cost effectively. So we're able to provide access to a lot of these unpublished historical materials from early Caltech. And like I said, that's a lot of what I will be drawing from today. Part of my role is to have conversations with Caltech faculty and other Caltech affiliated people about preserving the work that you've done beyond your publications, whether that is correspondence with colleagues or research notes that might be relevant to physicists, historians, and others in the future. I'm here for that, just to advertise the archives a little bit more. A couple of years ago, almost 2 years ago now, 1 month before Caltech started changing operations because of the pandemic, we opened an exhibit called Becoming Caltech, Building a Research Community 1910 to 1930 in a small exhibition space that we have in the Beckman Institute. That exhibit is still there, and we've sort of reopened and closed it depending on the particular access that we could give to Caltech people on campus. So we'll probably reopen it again, and we welcome all of you there. But we hope to reopen it publicly whenever we can reopen the building publicly as well. And to keep it open for several months so that it does get more of an audience than it had in the 1 month before we had to shutter it. But this particular period of 1910 to 1930 was of interest to us in 2020 because 2020 was the centenary of the name California Institute of Technology. And we sort of built the exhibit around the transitions in the institution that name change recognized. Today, I'm going to be talking more about the sort of 1920 to 1940 period and drawing a bit beyond that, and also presenting some of my own new historical research and some research by historians from the past several decades, actually, who have looked at early Caltech physics. And I'm going to be focusing on one particular building on our campus, And a second building will come into the story as well. The High Voltage Research Laboratory, which in its day was sometimes also called the Edison High Tension Laboratory, the High Potential Research Laboratory, or High Volts, and which is now the Ronald and Maxine Lindy Hall of Mathematics and Physics, right near where we are now. High Volts was the 5th new building on Caltech's campus. We moved to this campus in 1910. The 5th building after the central Troop Hall and Gates Laboratory of Chemistry, Culbertson Auditorium, and the Norman Bridge Laboratory of Physics, in which we stand now. And it was constructed in 1923. So this is going to be, the early 1920s are going to be a pivotal period for this story. I'll also be sharing with you some history, there we are again with High Volts, some history of the W.K. Kellogg Radiation Laboratory, which was built as an extension of research programs and other kinds of activities that were being carried on in High Volts. And so the two buildings have an intertwined history. And I'm going to be talking about the relationships between 3 different research programs that took place in these spaces. Research in high voltage electricity and electrical engineering, research in X-rays, and research in nuclear physics, represented here by 3 images that are very similar to each other, depicting the same space and even some of the same apparatus that carried over from one project to another. And a lot of what I'll be talking about today is the iterative development of infrastructure across these 3 research programs, so that each program built not only on the theories of those before it and the empirical results, but on the apparatus of those before it. And it was that material dimension that really facilitated much of the research that was done in the later programs. These research programs also depended in some crucial ways on the local conditions of Caltech, on our location in Southern California. So one of the sort of themes that I want to get at is the relationship of the laboratory to its environment. One of the purposes of a laboratory is to create a kind of placeless space where the same experiment can be done in this lab and replicated in this other lab. But there are particulars of what kinds of interests surround the laboratory in some of the stories here, what kinds of funding surround the laboratory that are geographically local and specific. And I want to tell some of those stories for High Volts in particular. Between 1907 and 1921, Troop Polytechnic Institute, the institute that became Caltech, reinvented itself. Astrophysicist George Ellery Hale moved to Pasadena to build and direct Mount Wilson Observatory. But after becoming a trustee of Troop, he turned it first from a school of manual and liberal arts into an engineering school. And then he recruited prominent scientists to make it also a research institute. In 1920, the institution recognized this transformation by changing its name to California Institute of Technology. Many of these transformations happened, though, prior to that name change. So in 1910, for example, Troop moved to its current campus, stopped admitting women as students, and laid off many of its faculty in order to reorient towards mechanical and electrical engineering. So this is also a pivotal moment. And in that year, we recruited the electrical engineer Royal Sorensen, who designed high voltage transmission equipment in Massachusetts and made a big move to come here in the days before frequent air travel. Attracted by Hale's reputation, by a Tournament of Roses booklet, which Troop mailed to him, and by the role of the humanities in educating engineers, Sorensen decided that this was a place that he would like to be. He himself suspected that Hale wanted him here because of Hale's interest in the transmission of hydroelectric power to cities, which Hale believed was crucial to Southern California. And so this is a sort of regional dimension to the makeup of Caltech's faculty at that time and to the research programs that were pursued here. When Sorensen arranged with the Public Electric Company to supply power to his laboratory in Troop Hall, then the central building on campus, now the site of the Turtle Pond, he heard disapproval from Troop's board, which overlapped with the board of directors of the power company's competitor, the private Southern California Edison Company. Both Sorensen and those governance relationships would deeply shape the future of not only electrical engineering at Caltech, but also physics. In 1909, Hale also began trying to recruit physical chemist Arthur Amos Noyes, his college teacher and friend, to come here from MIT, in part because Mount Wilson Observatory would benefit, as Hale wrote, from the improvement of photographic plates and various questions of solar and stellar chemistry. Key to Hale's vision for Caltech was cooperative research across disciplines, or what might now be called interdisciplinarity. It took him several years, but he did succeed in attracting Noyes eventually. In addition, Hale got closer to Robert Millikan, depicted here as well, through their collaboration during World War I, along with Noyes, Sorensen, and many other scientists and engineers, to build the National Research Council and bring scientists together to pursue research on subjects relevant to the war. Millikan, who had already completed his famous research on the charge of an electron at the University of Chicago, was commissioned in the Army Signal Corps as a lieutenant colonel and served as chairman of the National Research Council's committees on physics, optical glass, and submarine investigations. And it was in this time that Hale began persuading him to join troop. In 1917, he agreed to spend winters here, and 3 months a year wasn't enough for Hale, and Hale began strategizing to bring this prominent physicist to campus more. While these scientists were bringing science to the war effort in Washington, so this photograph was taken here on campus, but during World War I, they were spending most of their time in Washington advising the government, Troop was bringing its students to the war effort here on campus as well. All of our students enlisted as soldiers, and indeed they voted to make it mandatory for members of the student body. None deployed to Europe, although there were multiple casualties due to the flu, which came through campus during World War I. So in 1921, Hale brought together these elements: hydroelectric power, relationships with Southern California Edison Company, Sorensen, and Millikan, in a proposal. During this period in 1921, Millikan is making this decision about where to carry on his career, and he writes to his wife, Greta Millikan, in 1921, "I wish I could split myself up into parts. This is worse torture than courted damsels ever go through, for I could be perfectly happy with both suitors or with either of them." I'm not sure how strong an understanding Millikan had of those courted damsels. I'm sure some of them would also be happy with either of them, but this is the thinking that's been going on in his head. And so in this context, there's a correspondence between George Ellery Hale and Henry Robinson, both trustees of Caltech at the time. Robinson is also a director of Southern California Edison Company. And this is correspondence about sort of strategy for competing with the University of Chicago for Robert Millikan, and also perhaps competing with the Carnegie Foundation for Robert Millikan, because Hale had a concern that they were wooing him as their president. And Hale writes to Robinson, "If we might put one thing through, calling for $40,000 or $50,000, I believe we might hold him. This is the Edison scheme. The Institute could agree to run the plant if the Edison Company would give it, and I believe the company would get its money back in the form of new information regarding insulation and other problems connected with high voltage lines, not to speak of the advertising value. Millikan and Sorensen would make a strong team in such work, and Millikan would have the advantage of using enormous voltage to bust up some of his atoms. This possibility, which no other laboratory could match, is what excites him, and I am very anxious to give him this chance. When a man gets on the trail of the philosopher's stone, even if he isn't after gold, you can accomplish a good deal by offering it to him. A cheap building costing a few $1,000s, like the submarine detection laboratory, and a special transformer and other electrical equipment are all that are needed. If Millikan could meet one or two other Edison people, I believe we could convince them, or he could convince them." So in addition to his, I think there's a bit more there, yeah. In addition to his best known and most successful research programs in the charge of the electron and in cosmic rays, Millikan was interested in radiation and the transformation of elements, which both he and Hale colorfully described in the language of alchemy, as when Hale writes of the philosopher's stone. In 1904, Millikan had already written that the dreams of the ancient alchemists are true, for the radioactive elements all appear to be slowly but spontaneously transmuting themselves into other elements. In 1912, he and his student George Winchester used high voltage electricity to, they believed, produce hydrogen ions from aluminum. Millikan could continue that research at Caltech. In 1919, Ernest Rutherford similarly produced hydrogen from nitrogen, by bombarding it with alpha particles, although his result, unlike Millikan and Winchester's, achieved and retains scientific consensus. So Millikan sees high voltage as a key for these kinds of transformations, and sees this potential of working with the electric company, with Southern California Edison, to achieve high voltage as a way to do new kinds of experimental physics not otherwise feasible. When he applied to the Carnegie Foundation for funding, Hale described the lab as especially adapted for Dr. Millikan's researches on the breaking down of atoms and the resolution of the chemical elements into simpler components. Southern California Edison Company had a somewhat different interest in this partnership, which formed in 1921. In addition to sharing members of their boards of trustees between these two organizations, there was also a prior relationship with George Ellery Hale because Southern California Edison had supplied electricity for Mount Wilson Observatory in a partnership. There was a particular interest at Southern California Edison in very high voltage for its time, electrical transmission. High voltage power transmission began in California, wrote Sorensen in 1924. In no other part of the world is the transmission of power over great distances so highly developed. In 1921, Edison was planning to change their transmission lines from 150,000 to 220,000 volts. Such lines and associated insulators, transformers, circuit breakers, and other equipment would need to be able to withstand a massive surge from lightning, requiring new testing equipment and facilities. Hence, read a report, the necessity of producing lightning under controlled laboratory conditions. High volts would be the first lab in the world to produce 1 million volts. And so it's in this context that Hale writes to the president of Edison that Millikan probably wouldn't have come to Caltech if not for the offer of $75,000 by Southern California Edison to build this high voltage laboratory. And in that letter, Hale also writes that both he and Millikan are very interested in the Edison Company's plans for the Colorado River project, plans which show up in Millikan's own papers, although without a lot of context. So we have a couple of images like this that show up in Millikan's files on the high voltage research laboratory. This is an elevation map of the Colorado River. This is a map of what parts of the country are within 500 miles of some particular points on the river that could be dammed. The Edison Company had begun scouting the Colorado for hydroelectric dam sites in 1902. And in the 1920s, they were competing with the federal government for control over the river's power. Higher voltage transmission meant a dam could serve a larger region and find sufficient demand for the massive amount of electricity it produced. And so there was apparently some consultation of the Caltech scientists whose work we know for other things in thinking about this dam project. And there was also consultation in designing the high voltage research laboratory as a space to do both physics and testing of this high voltage electrical apparatus. Most of its interior was a single large room. Sorensen, for the purposes of this new facility, invented the cascade transformer, an innovation which was simultaneously made by others in Germany, and designed a 1 million volt model composed of 4 250,000 volt transformers, each of which weighed 22 tons to be installed in high volts. It stepped an externally supplied 15,000 volts up to 1 million volts of continuous current. In addition, the lab installed a surge generator, which produced an arc or impulse of very short duration, similar to that produced by a lightning stroke. Manufacturers were apparently skeptical that Caltech could actually afford their transformers, and it was only after Caltech announced that Millikan was joining full-time that General Electric and Westinghouse submitted competing bids. In 1922, Millikan accepted Westinghouse's, which of course then led to the manufacture of these transformers. The contract between Caltech and Edison took the form of a lease. Edison paid $1 to use the land for 25 years and agreed to invest $105,000 in the building and its transformer and to supply up to 10,000 kilowatt hours of electricity per month without charge. Construction ended up costing $35,000 more than that, which Caltech paid. Despite the lease form, though, both organizations had equal rights to use the facility. in Caltech's case for, quote, educational, experimental, instruction, and research purposes. Historian of universities Roger Geiger has written about this. He's written, the high tension lab was one of the relatively rare cases in its day of industry making a substantial contribution to enhancing the research capacity of a university. Perhaps of more significance, it demonstrated the organizational malleability of a research university in devising ways to accommodate the mutual interests of both patrons and faculty. And this lease was very different from Caltech's other fundraising of the time, which focused on a few foundations, but mostly on wealthy local individuals, including trustees of the same organizations like Edison, but as individuals. Most of the money coming into the Institute was not coming from other organizations. Edison hired the same architect Caltech employed for neighboring buildings, Bertram Goodhue, known for his Spanish colonial revival style. Millikan provided specifications, including the need for airflow because the electrical equipment would produce large quantities of ozone. And Edison engineers designed a steel frame, the second constructed in Pasadena. Goodhue designed the exterior, which used a diamond pattern to provide texture in the absence of windows, one of the features of the building that's been lost in its transformations as windows and floors have been added. The similarly prominent architectural sculptor Lee Lowry produced a relief over the entry, which conveyed the high voltage research performed within, another feature that's been lost over the building's revisions over the years. A historian much more recently in the 1980s, Robert Cargan, argued that Millikan's interest in radioactivity and nuclear transformation led him to his research in cosmic rays. That's something I can go into in more detail if you're interested. But that cosmic ray research often took Caltech scientists off campus onto mountains and other spaces where they thought they were more likely to detect the cosmic rays, and was less central to the work of the High Voltage Research Laboratory itself. It's not clear if Millikan ever tried to use high voltage electricity in the lab to try to take apart atoms again, as he believed he had done in 1912. But ultimately, that kind of work would come about through more complicated and indirect means. According to the February 1949 issue of Caltech's magazine, Engineering and Science, these facilities have been used to aid Southern California Edison in the development of high voltage transmission lines, to furnish lightning protection of oil storage tanks for the oil industry, another field of particular concern in Southern California, and to test insulators for numerous utility companies. The transmission lines made it possible to transmit electricity to Southern California from the Hoover Dam in Nevada, in its early days known as Boulder Dam, a federal project for which Edison ultimately controlled 9% of the hydroelectric capacity. Among the other innovations of the lab was a vacuum switch designed by Sorensen and Millikan, which took some time to commercialize, but eventually was manufactured for aircraft and other industries. And another use of this space was in public presentations. Sorensen regularly gave a public lecture and demonstration on high voltage electricity, with the latter portion taking place in high volts. In 1949, Caltech's magazine reported that the demonstration proved to have its usual strong draw this year, when on a rainy Friday afternoon, almost 1,000 people stormed East Bridge. Professor Sorensen obligingly gave his lecture twice, and the lab ran off 3 demonstrations while a special police detail coped with the crush. We also have a description of what these demonstrations were like from Caltech chemist John Roberts in one of our oral histories in the Caltech archives. He visited as a teenager to see these demonstrations long before he became a professor here, and described how the room was filled with all kinds of electrical equipment, enormous transformers and condensers and so on, big swooping insulators. It looked like Frankenstein's laboratory. Great transformers topped with big mushroom rings, you know, they used to shoot sparks off of. They would start an arc at the bottom of a transformer and it would grow in length and rise to the ceiling.
Excuse me, 1,000 people were fitted to 2 lectures.
I don't know. Maybe they didn't all make it into the lectures. I don't know. Maybe some people waited outside and were turned away. Because yes, I don't see a space in this building for 500 people either. But what we do have is the report that all those people were interested in getting in, at least, whether they actually were able to attend that time or not. So we have this description of these very exciting demonstrations. Roberts also says they charge up the condensers and shoot off big sparks and blow up some blocks of wood and stuff like that. This excitement did come with danger. In 1924, there were 2 serious accidents in the lab. One of them killed a man. I'm still doing some research in this area, so I don't know more than that. And that accident also shocked 2 others. Another severely shocked a student. And these accidents led to Assistant Professor of Electrical Engineering George Forrester writing to Sorensen and Millikan to advocate for improvements in safety procedures. He wrote that danger was created by, this is a quotation, overzealousness in prematurely exhibiting the laboratory to the public, the possession of keys to various buildings by any number of our undergraduate students, and ignorance on the part of the students of the potential dangers involved in operating any electrical apparatus. So things to keep in mind as we make our spaces safe now. Into this environment of excitement and danger came one particularly influential individual. Oh, there's just another beautiful image, also depicting the excitement and danger of the laboratory. One particularly influential individual who arrived in 1926, Charles Lauritsen, who was a Danish architect and sculptor turned radio engineer. He saw Millikan lecture while Millikan was traveling about the country giving presentations and decided that he needed to come study at Caltech. And he thought maybe he'd only spend a year here, but he ended up finishing a PhD in 3 years, staying on, becoming a professor, and spending the rest of his career here. Lauritsen completed his dissertation research in his first year at Caltech, research on cold field emission, producing a dissertation entitled Electron Emission from Metals. And based on the expertise that he developed from that, dealing with some of the same electrical phenomena at smaller scales, the second year he was here, he and Ralph Bennett began building the world's first 750,000 volt X-ray tube using the high volts transformer as their power supply. They then went on to build the first 1,000,000 volt X-ray tube depicted here, overcoming several technical barriers to extremely high voltage X-ray. Previous tubes had been limited to about 350,000 volts, and they came up with ways to protect the tube from electron backstreaming and achieve these higher voltages. And they did this while building tubes out of glass parts that had been designed and manufactured for other purposes. Specifically, this is a quote from his student and assistant H. Richard Crane, a recollection from the 1990s. He had a tube made out of a column of 4 5-gallon glass cylinders from gasoline dispensers. If you are old enough, you will remember them in all gasoline filling stations. Part of gas station design at the time in the 1920s and 1930s was to have the gas visible to the customer in glass tanks. And it was these same glass tanks that Lauritsen used to build X-ray tubes. In his 1930 patent application for these exceptionally high voltage tubes, Lauritsen wrote, "Radiation substantially the frequency of the gamma radiation from radium may be obtained from the tube embodying my invention. Such tubes can therefore be employed as the full equivalent of radium in the treatment of disease or for therapeutic purposes." Both X-rays and radium had medical applications since their discoveries in 1895 and 1902, and both were also subjects of wide popular interest. As Lauritsen was writing in 1930, many, including very visibly Marie Curie, saw radium as uniformly beneficial for health and as a source of energy that could invigorate the body. One could buy and drink radium water. And so this possibility of medical applications for the X-ray was a very exciting dimension of the work that was being done in high volts. And Millikan and Lauritsen decided to pursue this through a partnership with the physician Seeley G. Mudd. One of the striking things about this partnership that develops medically is that Caltech biologists at the same time were really steering clear of medicine and what we might now call translational research, and trying not to have those kinds of applied dimensions to their work. But physicists were very enthusiastic about medical physics. Mudd's mother, Della Mudd, had donated to form the Seeley W. Mudd Laboratory of the Geological Sciences in memory of Mudd's mining tycoon father. and during the Depression had let Caltech delay building it and use the interest on the donation to pay other debts. That is North Mud. South Mud, added in 1974, is actually named after the mud I'm discussing now, Sealy G. Mudd, who inherited his father's mining fortune along with his first and last name, but also studied medicine at Harvard and became a radiologist. Millikan enlisted the younger Mudd in a partnership researching the therapeutic effects of the million-volt X-ray tube compared to the lower voltage radiation already available in hospitals. And the Los Angeles County General Hospital began to bring cancer patients to high volts for radiation therapy. Although he was independently wealthy and didn't receive a salary, and indeed he donated money as well as his time to the project, Caltech appointed Mudd first a research associate in radiation and later in 1935, professor of X-ray therapy. And at the same time, we appointed another physician, Clyde Emery, assistant professor of X-ray therapy. So you can see among at least one familiar name, Linus Pauling, professor of chemistry, we have Sealy G. Mudd, professor of X-ray therapy. In 1931, Millikan pitched the project to another funder, cereal company founder W.K. Kellogg, who had a horse ranch in Pomona, California. Kellogg agreed to fund a new building specifically designed for radiation therapy and donated $150,000 to the construction and maintenance of W.K. Kellogg Radiation Laboratory. 5 days after he agreed to donate, construction began. So there must have been some plans in place already. Charles Holbrow, a physicist who has written about Kellogg, wrote, "It appears that Millikan underestimated Kellogg's potential as a donor. The next year, Kellogg donated his 700-acre horse ranch and $600,000 to the University of California. But the building that we got on campus from his donation contained a 30-foot X-ray tube, this treatment room for 4 patients, designed to have 2 sitting and 2 lying, and ongoing support for cancer research and therapy on campus was made by the Mudd family. Those contributions also supported the graduate students and postdocs who kept the facility running and who also had time to spare to conduct their own physics research outside of the medical domain. In 1936, though, the Mudd family money ran out. Millikan approached Kellogg, who attempted unsuccessfully to retrieve the ranch he had given to the UC in order to donate it instead to Caltech. And there's an ongoing dispute. That ranch is now Cal Poly Pomona, so Caltech never got it. To bolster the program, Millikan and Lauritsen brought prominent French radiation oncologist Henri Catard to Caltech and applied for funding from the National Academy of Sciences National Cancer Advisory Council. But they were trying to persist this program under changing circumstances in medicine. The relationship between radiation and health was changing in the 1930s, with high-profile deaths, including that of Curie herself in 1934. The pathologist with whom Caltech collaborated himself wrote to the National Academy that X-ray treatment seemed to be ineffective and even harmful to patients with prostate cancer, although in some cases it seemed effective for those with cervical cancer, among several other conditions. Millikan sought funding elsewhere, but in 1938, Sealy G. Mudd himself left Caltech, having treated 746 patients in Kellogg. He later became dean of USC's medical school and donated tens of millions from his fortune to fund buildings at dozens of colleges, including both South Mudd and Caltech Hall here on campus. This was the end of medical physics at Caltech. Meanwhile, for Lauritsen, radiation became the family business. Sigrid Lauritsen, the second from the left here, his wife, studied medicine at USC as the only woman in her class, earned her MD in 1936, and became a radiologist. Thomas Lauritsen, their son, studied physics at Caltech, received his bachelor's degree the same year his mother received her MD in 1936, and his PhD in 1939, and became a Caltech professor in 1946. And I, of course, picked this photograph because of the venue. Meanwhile, in 1932, physicists John Cockcroft and Ernest Walton built an accelerator at Rutherford's Cavendish Laboratory, which bombarded lithium ions with high-energy protons, successfully disintegrating a lithium nucleus into 2 helium nuclei. And this suggested a more general strategy for dismantling nuclei than Rutherford's earlier work, and thus further advances in 20th century alchemy of the sort Millikan had sought. In the US, 3 labs had similar resources. Merle Tuvey's at the Carnegie Institution in Washington, DC, Ernest Lawrence's at UC Berkeley, and Lauritson's in Kellogg and high volts. The field opened, recalled Richard Crane, in just the years in which money was the most scarce, the Great Depression. Therefore, improvisation was in order. Equipment made for other purposes was adapted. Glass cylinders from gasoline pumps, as I mentioned, insulators from power line switches, a magnet intended for a radio transmitter. The timing was right for me. Thinking my thesis would be in X-rays, I had just finished building a big 600,000 volt X-ray tube out of a big porcelain insulator. So we put a second insulator on top so it would stand even higher voltage. These porcelain insulators were available in quantity because Southern California Edison was still using the facility alongside the Caltech scientists, testing them for Hoover Dam transmission lines. The X-ray tube became a positive ion accelerator, and Caltech's physicists joined the founders of the new field of nuclear physics. Also on hand was an electroscope, which Charles Lauritsen had invented to measure radiation doses in the form of a small ionization chamber. By lining its inner walls with paraffin, the group now made it a neutron detector. The Lauritsen's group's first publications with the new apparatus in 1933 and 1934 reported the first production of neutrons using an accelerator by accelerating helium ions into beryllium. In the late 1930s, Hans Bethe and other theoretical physicists proposed that stars derived energy from nuclear reactions. Pasadena had long been a site for synthesis of physics and astronomy, and even particularly solar astronomy. Hale's own early research was on the chemical composition of the sun. When they read Bethe's work, Caltech physicist William Fowler said later, "For those of us in Kellogg, this was the dramatic event of our lives. What we were doing in the lab had something to do with the stars." And Kellogg became as well a key site for nuclear astrophysics. So the history of high volts suggests a number of patterns in the history of science. It was for its time an unusual site of corporate university partnership, a phenomenon which has become more common through sponsored research and again through shared facilities like the new Amazon Web Services Center for Quantum Computing, which I think is worth thinking about comparatively with high volts as a university corporate shared facility. And we might even regard high volts as one of the first chapters in the history of such arrangements. Perhaps unlike the Amazon partnership, though, the Edison partnership was deeply shaped by Caltech's local environment. It was the specific electricity generation landscape of Southern California, which motivated corporate participation. High volts and Kellogg were also the sites of the iterative development of research infrastructure. Across programs in electrical engineering, the physics of electricity and X-rays, radiation therapy, and nuclear physics, the tangible accomplishments of one program became the tools of another. As the US prepared to enter World War II in 1941, at Lauritsen's direction, Kellogg dramatically changed its priorities and focused its efforts not on nuclear physics, but on designing and producing rockets and proximity fuses. A large part of Caltech literally became a branch of the Bureau of Ordnance, recalled Fowler. It was such a large part that the rocket program alone had a budget 19 times that of all of pre-war Caltech. So another lesson of this history, perhaps, is that political forces, and especially war, can dramatically change the trajectory of research groups, even reorienting them towards programs that don't employ their specific expertise, but rather their more general mathematical, scientific, and engineering prowess. High volts retained its unusual single-room architecture until 1960, when Caltech renovated it into the Alfred P. Sloan Laboratory of Mathematics and Physics, producing a more conventional internal structure with windows and 5 floors of space, including new basements, rather than a single large room. By this point, it had a storied career contributing to electrical engineering, nuclear physics, radiation therapy, spectacular public demonstrations, and even science we might call alchemy. Thank you.
Thanks, Peter. Wonderful talk. So open the floor to questions from the enormous audience here, and maybe can we get this?
I think we can just stop sharing and then we should be in Zoom normally.
Yeah, I was just going to check on that.
Absolutely.
So if people online have questions that they'd like to ask in the chat window, please go ahead. And otherwise, are there questions from here while we're waiting for typists? So I had one little thing I noticed. You had a picture of Sorensen that says circa 1910. But the calendar behind him.
Ooh,
from
thank you.
1918. So
Well,
it's-
perfect. You've dated it for me. I appreciate it. I will put that in our metadata. That's fantastic. Thank you.
Yeah, so the other famous example of Caltech industry partnerships is actually Milliken's son. I believe that what's now the Art Center was the hypersonic or transonic wind tunnel, which was built across from the power station for obvious reasons. I think the power station even added a couple of extra generators to provide the power. So that was, I think, many local aircraft companies in partnership with Caltech.
Absolutely. Absolutely. Yeah. Clark Milliken.
But, no.
Yes. Yes, and I don't know this nearly the same level of detail about that project. I think there are threads of early aeronautics in Judy Goodstein's book Millikan School, which is of course a source for some of this talk as well. And we had some earlier wind tunnel development and earlier airplane development in our exhibition.
But I don't
And
know whether that
absolutely.
was explicitly a partnership. I know that
Absolutely.
the
But yes, that's right. That wind tunnel, I think, has also something in common with some of these projects in high volts, like the X-ray tube, in that it has these superlative claims around it. I think it was the largest wind tunnel of its time. So absolutely, that was a similarly ambitious project.
Hey, Peter, we have a question from David Hitland on Zoom. I'm going to ask him to unmute.
Yeah, I think there was, it's not really a question, it's a comment. You mentioned that high volts had gotten to 1 million volts, the only place with 1 million volts. So the interesting distinction to be made is when Cockcroft-Walton made their generator and got to 1 million volts, they got a Nobel Prize. So what's the difference? The difference is AC versus DC. Because of the history of power generation, what was going on at Caltech was AC transmission. And the Cockcroft-Walton generator turned AC into DC, so you could make a beam and accelerate a well-defined beam of particles and do nuclear mutation. So that AC-DC distinction is actually rather important in the development.
That's really helpful. Thank you. I have seen the physicists who are working in high volts write about AC as a constraint in their work, and that explains exactly how it was a constraint. So I appreciate it.
We have another question here from Brad Philippone. I'm going to ask him to unmute.
Hi, Peter. Thanks for the nice talk. I wanted to mention, you mentioned at the end about Hans Bethe and his connection with the stellar creation of energy. And he actually, I worked in Kellogg. I have worked in Kellogg for many years. During the late 80s and 90s and even 2000s, he came to Caltech to get away from Ithaca in the winter, and did a lot of his work associated with, some of it associated with LIGO, working with Jerry Brown at Caltech.
That's great to have that connection be more concrete, that it's not just people writing articles and reading each other's work, but visiting, and that it persists into such a recent period of the history of physics. I had not known that. I appreciate that. Thank you.
He also worked on the theory of supernovae. So, any other questions?
No other questions on Zoom at the moment.
You are welcome to ask questions about other areas of Caltech history, although I will not have any technical precision on them, most likely. But if you choose to play Stump the Archivist, that's always a game I'm up for.
Yeah, and when things are open, I encourage people to go visit the archives. It really is a wonderful place. If you ever wanted to see first editions of Principia or Galileo and other things. There's really a marvelous collection there. Plus, of course, the people who are here. So
Absolutely. Yeah, we're happy to have visitors and to show off either the Caltech history or the longer history of science. In addition to the exhibition on the first floor of the Beckman Institute, you're welcome to make an appointment to come down to the sub-basement and see more.
We have another question from Brad here.
Peter, you showed a picture of a treatment room. I was wondering, do you know actually where that was in Kellogg?
I don't know where it was in Kellogg, and it's a picture that I would like to learn a little more about. In fact, there's this article that was published in Physics Today in the 1980s by Charles Holbrook on Kellogg that's very useful, and he reproduces that picture. And he attributes it to the Caltech archives, but I have not found it yet in our collections. So I pulled it from his article instead. So when I find it in our collections, there may be some context there that I can use to place it, or maybe Alan knows.
I can let you know several of the offices in I guess the basement level of Kellogg, which I had an office once there, have these large electrode connections, which clearly were for some sort of treatment. So it may be there, or it may be one floor above. I'm not sure.
Absolutely. And I've just been reading a little more about the sort of mechanics of the therapy. And there were, I need to read more on this. There were apparatus that were inserted inside the human body. So there would have to be some sort of conduit for attaching those smaller apparatus to the very large X-ray tube.
Brad, the treatment rooms, there were 3 of them, are on the level Kellogg Radiation Lab that used to house the Xerox machine and a small video conference room set up by Bob McEwen. And in the middle room has the file cabinets in it. Those 3 rooms were the treatment rooms. And if you walk into one of them and look at the floor, you will see the round circle that Peter showed in one of his photographs.
Terrific. Thank you, Alan. I think we may need to, at some point, do a historical tour of Kellogg. High volts, we don't have any of the sort of original interior there to give a tour of, but Kellogg we do.
There's American Medical Association gives plaques like the American
Yes,
Physical Society.
I don't know if they do.
Because I think the plaque for the positron is on the wrong building. It's on Bridge instead of on Guggenheim, where he actually discovered the positron, but maybe Kellogg deserves a medical plaque.
What was he doing at Guggenheim?
He had his, the lore, people seem to think he was doing it here, but he needed the power supply for the wind tunnel in order to get enough power for his electromagnet. To deflect the positron. So he was actually on the roof of Guggenheim that they discovered the positron. That had nothing to do with the building where the plaque is. Again, it's all about electricity supply.
Absolutely. Yeah, that has been one of the threads for me, is that having electricity in volume, and as one of you pointed out, whether it is AC or DC, make a tremendous difference for what kinds of experimental physics can be done. And so much of the effort to build a laboratory that could do more was very simply about building a laboratory that had higher voltage. And so then for other kinds of research, that matters as well.
Okay, well, if there are no more questions, let's thank Peter again for a wonderful history of physics here.
Thank you for having me. And I will hang around a moment, both on Zoom and in person, in case anyone wants to talk.
So Alan, are there historical blueprints or something that you were looking at, or where does one find these interesting nuggets?
If you, I've just been standing in the building now for 42 years, and this stuff just comes to me. I've always been fascinated by I was hired into Kellogg in 1979, and I've always been fascinated by its history. So I've just been sensitive to little facts as they come drifting by. And Peter, I'd love to sit down sometime and share that.
Absolutely, I would appreciate that. Thank you.
In fact, Brad Philippone and I have in storage a, who did the hand drawings of the Palomar telescopes?
Russell Porter.
We have a Russell Porter drawing of one of the accelerators in the Kellogg building. And someday after we're finished displaying it in physics, math, and astronomy, we'll turn it over to the archives.
Absolutely. Yeah, we also could work on doing a reproduction like we did for the Porter drawings, the Palomar drawings. So there's certainly possibilities there to see if we can preserve it as effectively as possible, but also display it.
I think we still have that, Alan. I think I know where that is. We hung it in the hallway, but we remodeled after the fix up of Linde. We had to take it down.
Right. I think I have it in storage.
You have it. Okay.
Yes. So what I'd like to do is to, as Peter suggests, reproduce it and hang the reproduction someplace near your research.
Great. I would be happy to collaborate on that. And yeah, the Porter drawings are an incredible collection because the Palomar drawings are the best known, but he did so many drawings for campus facilities as well. And so we have, at least dozens of drawings of things that either were built or never were here in Pasadena. That could be its own talk, the Russell Porter Beyond Palomar.
Yes.
I think Russell Porter could be the whole course.
It could, maybe for the new visual culture program in HSS. Absolutely.
Your talk was very tying together separate items that I knew.
Oh, good.
How did they fit together?
I'm glad to hear that. That's part of what I'm trying to do with it.
A separate issue is these local businessmen. What was their interest apart from magnetism and Hale's magnetism?
Yes.
Contributing to this venture?
Yes. So I think part of it was that. So I think some were involved before Hale, and so they were invested in a local institution. They might have been trustees of Troop when it was still focused on the manual and liberal arts, and having a local college was meaningful to them. But Hale, I think, persuaded people who stayed involved that it should be an institution of global excellence and not only a local institution. And so I think that some of it was a parallel set of reasons for Edison. So Edison has a very concrete set of things that they want to do in this space, but they're also interested in building up a workforce of technically trained people who they can employ, who they can bring in as consultants, and so on. I think that many of the businesses that had their leaders, their managers, their owners were wealthy Pasadenans, were similarly interested in technical expertise as a source of economic growth. And so you can think about Huntington and electric rails, or both the channeling of water through aqueducts or of electricity, or the aerospace industry, the aeronautics and then aerospace industry. These are things which a technical institute can provide the expertise for that then they can capitalize on. And I think that was part of the motivation as well. Absolutely. But I think part of it is the magnetism of these particular charismatic individuals. Because some of these people like Kellogg, who made his fortune on cereal, was not actually particularly interested in the physics, but he was interested in the medicine. And so part of it was appealing to that interest. Well, thank you.
The quest for high voltage did not end with Edison. Ultimately, we went on to achieve 7 million volts on campus in the early 80s. using the one of the accelerators operating inside of tanks with compressed nitrogen.
There's a few threads immediately after this. One of them is the construction of, I guess actually during the period I talked about, the construction of the first Van de Graaff generator on campus and electrostatics. And so there's a particular thread there that I sort of didn't include. So yes, I think that there's the story of high voltage within and beyond the building named after it has some more threads to it. Where was that 8 million volt facility?
It was in the sub-basement of what is now called Lind Hall. So it was the sub-basement of Sloan.
Yes, yes. So still the same building, but a particular floor rather than the whole building.
I think, didn't it extend under the ponds now? I sort of remember there
No,
was
that was the Pelletron, Sterl.
separate.
The EN, the accelerator that Alan's talking about was called an EN tandem from High Voltage Engineering, I think, Alan, is that? Yeah, the company, right.
It's actually at the same time they were knocking holes in the walls of Sloan to make windows, they dug in the adjacent garden, they dug a deep hole and put in the Van de Graaff accelerator that Brad mentioned. That was in 1960.
Wait, no. Well, oh, you mean the EN, yes.
EN, yes.
Yeah, the Pelletron was in 81, I guess, right? 80.
81. But these were not there were earlier accelerators in Kellogg that were vertical machines.
The artist you mentioned that's what he drew. He drew one of
Yeah.
these vertical machines, which was actually on the, I guess the second and third floor of Kellogg is what it where it
Sort of
existed.
confusing.
Right.
Well, we're happy to bring more records of all of this into the archives if they're out there. So that's another conversation I'm happy to have aside from the research. So please.
So
Please
Brad
feel
or Alan, do you know where Ward Whaling did his experiments on the triple alpha? Was that using one of these particular machines?
Yes, it was one of the vertical machines that came into what used to be called Room 100, I believe. They moved the magnet in so he could do his famous measurement of the what is it called? So the origin of life, I think they sometimes call it.
I mean, it's the great bottleneck of getting triple alpha decarbonized.
Right.
Special resonance.
It has a very famous right.
The anthropic principle, I guess it was Hoyle's anthropic principle prediction.
Right. If it doesn't exist, we don't live. We're not here, right? Yeah, I believe that was in what is the first floor of Kellogg, but from one of those vertical machines.
Yeah, because it would be nice if we could sort of have a little, plaque memorializing some of these important discoveries. I mean, that was a really important one, and I think the average astronomy student across the street has no clue that was measured there here.
Right, the Hoyle state, yes, is certainly very interesting.
Well, the positron plaque was one of the very first plaques on campus commemorating any kind of discovery in a way that was visible to the public walking by. There are very, very few such signs like that on our campus. I was glad to see experimenting with one of them. I'd like to see more of them.
Probably need APS to get involved. That's something they could, think about.
You know, for formal plaques, I mean, I think we can always create a little poster to put next to a door of each building that had something interesting in it without, I mean, the APS plaque looks nice, but we can
Or even
photograph.
less conspicuously inside the building where it says, in this space formerly there was, and describe what
Right.
interesting things happened there. Especially in places like Lind Hall, where you can actually see, we've left some of the original high volts architecture visible, hints of it. So a little plaque in one of those places would be very wonderful.
And since it was only one room originally, you only need one plaque because you're always in that room.
Well, I think the synchrotron building deserves another to explain
Mhm.
the
Right, right.
telescope and the synchrotron and LIGO and how
Absolutely.
many satellites and things were assembled there.
Absolutely.
Peter, I had a question. You showed this nice a relief on the front of Sloan / Lindy.
Yeah,
Was that destroyed in the when did that go away?
I have a picture of it being destroyed. So 1959.
Ah, okay.
So here's the
I really enjoyed it, but I certainly oh my gosh. Oh my
Yeah.
gosh.
Yeah. So yeah, that was part of the Sloan renovation, and I don't know why. I mean, maybe we have some documentation of the decision, but probably not. Probably. But yes, let me show the relief again because it is beautiful.
Yeah, it was beautiful. Right. I certainly had never seen that version before. Yeah.
A little bit like the one on the entrance to Hale's home in San Marino, where he has
Ah.
Egyptian sun god.
And I don't know if it's the same sculptor or not. I think it's the same sculptor as some of the work on Guggenheim. So which does still exist. But I'm not sure about that.
I have a blueprint from prior to the construction where it was clear that the blueprint was a notional design of what a kind of a proposal for what would be provided there in greater detail later.
So why did it have to be destroyed? I saw that horror.
Not a clue.
Okay.
Oh, yeah.
Well, I think they moved some, I guess there was a renovation of, I forget which building, but the arches
Oh, yeah.
were
Well,
moved. I guess maybe nobody thought it was important to preserve these.
yeah,
Maybe the other
exactly.
ones.
I don't think this one was kept in one piece. Yeah, the arches that are now I'm not remembering the building. They're
Between the biology buildings.
exactly
They used to
between
be
biology
somewhere
buildings.
else.
Those were part of Troop Hall, originally
Right.
Pasadena Hall, which was the first building on the campus. And it was damaged in the Sylmar earthquake in 1971
Right.
and was torn down after that. So those arches were salvaged, and a couple other architectural details that are also in the parking lot behind. Loma knows.
If I may interject,
Loma knows more about Caltech.
the arches were only saved, I think, originally because there was a deal with the city of Pasadena that they would be saved, and they were languishing in a yard for years. I mean, we weren't hanging on to them with the assumption that someday they would be included in a building that would be built in the future for the city. And nothing ever happened. And then I don't know what the final decision was to bring it all back and put it together. But originally, that might have been destroyed as well, had it not been for the fact that there was this discussion that the city was interested in it.
Thank you, Loma. Yes, I had forgotten that context.
If there were some wonderful way to show how space in a building had evolved over time, it would be make an interesting history of Caltech. Because the space in Kellogg that used to support high voltage research went on to nuclear physics, and now it's becoming math space, for instance, and it's difficult to sometimes wrap your head around that.
And the
Yeah,
synchrotron lab certainly has a long history of changing what it's doing.
Absolutely, yeah.
For that, we've started a web page internally at the division to depict the history of all the things that have gone on in the high bay, synchrotron high bay area.
Great. Yeah. I mean, I could imagine campus-wide some uses of animation or of more interactive web technology to allow you to pick a year and see what was happening on the campus at that moment and drag it forward and back on a timeline. It'd be a project, but it would be interesting.
I think I read somewhere.
The hole that was dug to support the EN tandem accelerator, eventually it was cut up and hauled away, and 2 or 3 more labs have used that space in the intervening years.
I was going to say this, the synchrotron high bay, I think was actually, I read somewhere, the second large building in the United States to have air conditioning.
Aha.
Because for the grinding the mirror, they needed to keep a constant temperature, and Carrier had invented the air conditioner the year before, and Russell Porter and Hale, I guess, instead we're getting one of these new things. So.
Well, thank you, Peter. I really appreciate these kind of historical excursions into Caltech's past. I really, really do.
Thank you for joining us, Alan. It's good to see you. I'll look forward to seeing you again soon.
Thanks. Bye.
Bye. Great to meet you.
Bye, everyone.